In this video, we'll derive a formula for the derivative of a to the x, where a is some constant real number. So I want to first recall our formula for the derivative of e to the x. So the derivative of e to the x is itself. It's e to the x. And we also know how to do the derivative of e to the stuff. If I have e to the stuff, we use chain rule for this. And the chain rule says, so this is by chain rule, and it says, well, you get e to the stuff, because it's the derivative of the outside thing, the e to the x part, but you keep plugging the same inside function, the stuff, in. So that's why we have the stuff in the exponent. And then times the derivative of the inside, the derivative of the stuff. Okay, so those we know. So I want to take the derivative of a to the x, where the a doesn't have to be e anymore. It could be some other number. So my idea is going to be to make a to the x look like e to the stuff. Because if I can do that, I know how to take the derivative of e to the stuff. Okay, so there is something that I want to note. This is going to be some algebra review. And it's that if you do e to the ln of a, that is just equal to a. So I'm going to move this over. E to the ln of a is just a. And this has to do with the fact that e to the x and ln of x are inverse functions. So what we're doing is we're sort of taking a function, and within it you're plugging in the inverse. And when you do that with some number, the inverse and then the function, they sort of undo each other, and you end up with just a. And that's what this is saying, with the specific example of where my function is e to the x and the inverse function is ln. All right, so now I want to get a to the x. So let's raise both sides to the x power. So we'll do a to the x. And let's also do this side to the x power, this whole thing to the x power. And power to a power means you multiply the powers, like this. So you get e to the ln of a times x. Now let's take the derivative. So now we'll take the derivative. Now we'll do the derivative. So we have e to the stuff, and to get that derivative, we need the chain rule. So by the chain rule, when we take the derivative of a to the x, this is going to be the derivative of e to this stuff. And that's going to be e to that stuff, ln of a times x, times the derivative of that stuff. So times the derivative of the stuff, derivative of ln of a times x. Okay, so this is going to be equal to e to the ln of a times x, and then times this derivative. But one important thing to keep in mind is a is just some number. So ln of a is just some number as well. It's just some constant. So this is kind of like taking the derivative of 4x, or derivative of 7x. The derivative of 4x is 4, or the derivative of 7x is 7. In the same way, the derivative of this constant times x is just going to be that constant. So it's just ln of a. Okay, and we know what e to the ln of a times x is. E to the ln of a times x, let me put this in a different color actually. E to the ln of a times x was here, and that was a to the x. So that we get that this is a to the x. In fact, let me just write the rule. This is a to the x. So thus, what we've just shown that the derivative of a to the x is equal to a to the x times ln of a. Let me actually write ln of a first. ln of a times a to the x. I'm going to box that. So that is a key derivative rule. And let's highlight that in yellow. All right, we now know a formula for the derivative of a to the x, where a is some arbitrary real number, not just e. So one quick thing to notice about this is, well, does this formula still work for e? Because it's supposed to work for any real number a. Well, if a was e, then the a to the x part becomes e to the x. And notice that the ln of e, the ln of a part, ln of e is just 1. So you'd get that the derivative of e to the x using this formula is just 1 times e to the x. And that's correct. That's what we expect. All right, so we have this formula for this derivative. What would the derivative of a to the stuff be? What if I have a to the something more complicated? Well, I know this is going to involve a chain rule. And chain rule says, well, take the derivative of the outside function first. So that's a to the x. When I take the derivative of a to the x, I'm going to get ln of a times a to the x. But chain rule says, wait, don't just write x there. Plug in the inside stuff. So in this case, we'd plug in that inside stuff. And then chain rule says, well, okay, then multiply by the derivative of the inside. Multiply by the derivative of the stuff. And here we have a formula for the derivative of a to the stuff, not just a to the x, involving chain rule. All right, so let's do some practice problems. All right, so example 6, part A says, compute the derivative of 2 to the x. Okay, so this is no chain rule needed. This is just an a to the x type thing. And the formula says, well, this should be ln of a, in this case ln of 2, times a to the x, which is, in this case, 2 to the x. And that's it. That is my derivative. All right, so that one wasn't bad. Part B says, what's the derivative of 2 to the secant cubed of x? Whoops, I have 2 to the stuff, not just 2 to the x. So we will need chain rule. And the chain rule says, well, take the derivative of the outside function first, which is 2 to the x. It's secant cubed, which is getting plugged into 2 to the x. So the derivative of the outside thing is going to be ln of a, ln of 2, times 2 to the, but I don't write x because I keep writing the same stuff. So I keep writing secant cubed. And then I got to multiply this. I got to multiply this by the derivative of the stuff, derivative of the inside. Derivative of secant cubed of x. Okay, and for that derivative, I am going to need the chain rule again. Chain rule again because this is secant of x being cubed. So the inside function is secant. The outside function is actually x to the third. So that's a chain rule scenario. All right, so let's see what we have. This is going to be ln of 2 times 2 to the secant cubed of x. So now when we do the chain rule, it says, well, deal with the outside part first, which is the power. The power comes down, and then you subtract 1 from the power. And when you do that, the inside part stays the same. So I keep writing secant of x there, and then we do the chain rule step, which says, well, now take the derivative of the inside function. Take the derivative of the secant x, which is secant x times tangent x. And let's close that bracket, and that's our answer. I'm just going to simplify one thing. This is ln of 2 times 2 to the secant cubed of x. Let's see, and then I got times 3. I'm going to rewrite this secant of x being squared as secant squared x. That's secant squared x, and I can multiply by this secant x to get secant cubed x, and then times tangent x. And I would leave it like that. That is my derivative. So in terms of our goals, we finished the last goal for this section, talking about how we evaluate the derivative of a to the x, where a is an arbitrary real number.